Okay, hello everyone, and welcome to KITE Research Round. It's my great pleasure to introduce our speaker today, Professor Emilia Ambrosini. Dr. Ambrosini is an assistant professor at Politecnico di Milano in the Department of Electronic, Information and Bioengineering, and she's been there since 2017. Her research is focused on the development and clinical translation of novel methods combining functional electrical stimulation and robotic systems for rehabilitation and daily life assistance for individuals with neurological disorders. The title of Dr. Ambrosini's talk today is How to Foster Motor Recovery with Functional Electrical Stimulation, 2 practical examples for upper and lower limb. Before we start, just a reminder that you can type in your questions in the Q&A box during the talk or at the end. And now please join me in a virtual round of applause to welcome Dr. Ambrosini.
So thank you for the introduction. Thank you for the invitation. And so I will just start. I will hope that, okay, I will skip the first slides because have been already introduced. I just want to mention that my background, I'm a biomedical engineering with a PhD in bioengineering. I'm pretty sure that all of you know that stroke is the first most common cause of death and the main cause of acquired adult disability, and that about 80% of stroke survivors is affected by hemiparesis. That means that they have an affected arm and an affected leg. So from the lower limb impairment, these affect mainly walking ability, and the recovery of walking is the main goal, therefore, of stroke rehabilitation, while the upper limb impairment compromise the independence of stroke survivor in performing activities of daily living, having a strong impact then on their social and occupational activities and overall quality of life. This is the typical rate of recovery after stroke. So there is the stroke onset, then a very an initial phase of first days and weeks in which there is a spontaneous recovery that is really a little bit unknown already what is going on during this phase. And then there is this slighter with this improvement that prolong up to 6 months, but even after that. So we are already, it's established then that recovery does not stop after 6 months. And even in the chronic phase after stroke, it's possible to achieve improvement. And why improvement occurs after stroke? This is based on the neuroplasticity that is defined as the changes in the strength of synaptic connection in response to either an environmental stimulus or an alteration in synaptic activity in a network. And neuroplasticity can be adaptive or maladaptive to recovery. Indeed, not all changes in the brain have a functional significance. And what we would like to do and what we aim to do every day is with the design of rehabilitative intervention is to foster learning-dependent mechanisms of neuroplasticity in order to achieve long-term benefits and so long-term improvements. So several elements have been described in order to drive neuroplasticity, in order to improve these neuroplastic changes of our brain and these characteristics of our brain. And in this slide, I would like to summarize the majority of the elements. So it is important to practice a functional and goal-oriented training. The intervention should be performed as soon as possible, so early intervention. It is important to practice a high amount of training, so high intensity training, repetitive training, so number of repetition. The training has to be individualized based on the specific characteristic of each patient. It is very important that the subject himself contribute voluntarily during training. It is important to engage the subject, and then rewards, interactive and engaging tasks are very important. it is important to augment proprioception and to provide biofeedback that could be acoustic, visual, different type of biofeedback. In this picture, technology can play a very important role. Indeed, technology-aided intervention assure high-intensity, repetitive, and task-oriented training. They can be customized on each single subject, so technology can help in order to design individualized training. They can reduce the effort of the physiotherapist. They can assure to perform a training with a very high level of safety. Also, they allow to assess motor performance during training. Also, it is possible to combine different types of technologies in order to include many of the elements I have described before that has been shown an effect in driving neuroplasticity. And then early intervention, thanks to the help of technology, technology-based intervention, thanks really to the use of technology, can be applied very early, even for very severe patients, because technology can help them in performing tasks. So technology can play an important role in order to drive neuroplasticity. But which type of technologies I'm speaking about? There are many types of technologies in rehabilitation, starting from brain stimulation, brain-computer interface, virtual and augmented reality, robotic devices, and functional electrical stimulation. Today, actually, I will not speak about everything, but the examples I will provide you are based on these two types of technologies. So FES on one side and robotic devices on the other. So let's focus on these two elements and just start first from functional electrical stimulation. I'm pretty sure that all of you know what FES is. So I'm really fast into the introduction of the topic. So FES consists in the delivery of low power electrical pulses to generate muscle contraction and produce goal-oriented and functional movement. The main advantage of using FES is that we can augment proprioception, and this is important as this is important for neuroplasticity, and so it's just what is usually called as central effects. And also FES induce active muscle contraction, which results in a series of peripheral benefits, so increase of muscle tone, decrease of muscle spasticity, decrease of osteoporosis, and many others, cardiovascular benefits, and so on. The main disadvantages of FES as a technology are the difficulty in control due to the nonlinear and time-variant system that is our muscles, and the fast and sudden occurrence of muscle fatigue due to FES compared to voluntary contraction. When we speak about FES, we have many clinical applications that has been proposed since the first one, which is the foot drop stimulator introduced by Liberson and colleagues in 1961. And FES has been actually used clinically both as an assistive device in order to substitute function or as a therapeutic intervention to facilitate the restoration of volitional movement. And in this context, the application really starts from foot drop stimulator, but there are many of that. So multi-channel FES system for supporting standing and walking from spinal cord injured people, but also for stroke, upper limb neuroprosthesis for grasping, hand opening and closing, and FES cycling. So cycling is induced by functional electrical stimulation. And what I want to focus now is about the use of FES cycling in the recovery of stroke patients. Why FES cycling for the rehabilitation of the lower limb of stroke patients? Actually, cycling is characterized by an activation pattern which is very similar to walking. That is, as I said before, is the main objective of stroke rehabilitation for the lower limb, but does not require standing balance. So it can be performed in a very safe situation, even soon after stroke. So as soon as the situation is stable from a medical point of view. And these allow to perform an early intervention that is with the final hand with the final aim of gait recovery. FES cycling has been used for rehabilitation of stroke since 2010, and in a recently published systematic review of literature that I published on clinical rehabilitation in 2020, we have reviewed the literature and we have found 7 randomized controlled trials evaluating the efficacy of FES cycling in subacute stroke survivors. So overall, these 7 studies involved about 270 stroke patients with a mean age of 62 years and about 30 days after stroke, so in a very acute phase. And here I just want to summarize the results that we have found for the primary outcome that was identified as the ability to walk at short distances. This is the forest plot. I don't know if you are familiar with that, with this type of plot, but here are the studies that we have found. And this represents the mean effect of each of the single study with the respective confidential interval. And overall, this diamond here represents the combination of the results of each individual study. And overall, we could find a significant effect in favor of the experimental treatment that in our case was FES cycling with respect to control treatment that was usually standard physiotherapy for stroke rehabilitation. So there was a significant better improvement in terms of walking at short distances for subjects, for participants who were involved in the FES cycling treatment, but this improvement was not found to be clinically relevant. So we did not achieve the minimum clinical important difference for gait speed that has been established to 0.16 meter per second in stroke survivors. So among these studies, you have seen that some of that are carried out by group. And so I would like now to focus on one of these studies. So this is one of the studies, this one published in European Journal of Physical Medicine Rehabilitation in the same year. And this is a randomized controlled trial that was included in this systematic review. I want to mention, and I will now speak a little bit more about these studies. In these studies, what we proposed was a multimodal intervention that combined FES cycling and balance training. Why we do combine, so which was the rationale for proposing this type of intervention for subacute stroke survivors? So first of all, as I said before, we propose cycling since it is characterized by a similar locomotor pattern with walking, but does not require balance, standing balance. So it is safe to apply in a very early phase after stroke. We added FES in order to improve cortical revitalization and neuroplasticity thanks to the augmented proprioception induced by FES. We also added a visual biofeedback in order to maximize patients' motivation. And then we combined balancing exercises that was proposed in a second phase of the intervention. I will explain it in a while with a little bit more of details in order to recover standing balance. So the idea was to propose a 2 phases intervention. I think it's here, yes. So here is the study design. So we had a control group performing 90 minutes of standard physical therapy. And then we had an experimental group. And this experimental group performed 20 minutes of cycling training or balance training, and then 70 minutes of standard physical therapy, so the same as the control group. So the amount of training was the same for the 2 groups, but 20 minutes of the total 90 minutes that were foreseen for the control group were devoted to this experimental intervention. And the intervention was designed in this way. In the first 3 weeks, every day, so for 15 sessions, the patient were performing cycling training with augmented by FES. And in this plot here, you could see the stimulation ranges that were used in order to synchronize FES with the cycling movement. And in particular, we stimulated the quadriceps, the biceps, the hamstrings, the tibialis, and the gastro, and the gluteus for both legs, so both the affected side and the unaffected side of the patient. Also, we were asking the subject to, on the top of FES, to voluntarily pedal, and we show a visual biofeedback based on the force that we measure independently with two force sensors, which was placed at the pedal. We measure the force, the tangential force produced by each leg, and this was shown as a mean value for each revolution to the subjects in order to show them what the real work that they were doing with the left side and with the right side. Of course, I want to mention that, as I said before, we stimulated both sides, but the amount of stimulation was unbalanced. So the affected side received more stimulation, more intensity stimulation than the unaffected side. And during training, the subject was asked to try to pedal in a way in which these two bars were as much as similar as possible. After 3 weeks of training, instead of cycling training, the same subject of experimental group were involved in a balance training using a balance board and with visual biofeedback showing the center of pressure, so with different exercises in which they were asked to move the center of pressure with respect to some specific targets. So weight shifting and just standing posture and so on. So the idea was that in the first phase, when they were still not able to stand, they were performing cycling training plus FES in order to activate lower limb muscles. And then in a second phase, after the first 3 weeks, they performed our 3 weeks in which they were training on standing balance, both static and dynamic balance. And the main goal was, the main question that we had was if this type of intervention was more effective than standard physiotherapy in improving gait performance at the end of the training. So our main outcome measure was, our primary outcome measure was actually gait speed. We also perform a final, of course, assessment. So patients were assessed at T1, so at baseline, after 3 weeks. So when we change the intervention, after 6 weeks, and in a follow-up session about 5 months from the end of the intervention. And at the end, we recruited 68 subacute stroke patients that were randomized into 2 groups, so the experimental and the control group. And in this table, we summarize the balance, the characteristics of the participants at baseline. So this is the age. So the patient was quite old, about 74 years in average. The time to stroke was very, very short, so about 2 weeks after stroke they were recruited. And there were kind of balance between male and female, and for sure balance between the 2 groups. We had more ischemic, very hemorrhagic, as this is kind of typical. The affected size was almost balanced. And we had few participants that were not able to walk at T0, and this was a little bit unbalanced with respect to the control groups, in which we had more subjects not able to walk, although the p-value was not significantly different between the 2 groups. And this was the gait speed, so centimeter per second was about 65 in the 2 groups. So what we could see that the group was somehow balanced at the beginning of the intervention. And these slides here summarize the results that we achieved. Here are reported the main outcomes. So as I said, the primary outcome was the gait speed. And then we measure also the functional independent measure, the motor subscale, the motricity index for the leg, and the Berg balance scale in order to evaluate balance capability. And as you could see from the results, so this was so some thinking focusing on this p-value in terms of time, we could see that both groups significantly improved at the end of intervention, as we expect. So we are just in the very acute phase after stroke, so we expect that all subjects improved, but we did not find any interaction effect. So from this table, we could not say that our intervention group was superior. So we could not find any statistically significant difference between the 2 interventions. So this means that the 2 interventions we could not say that our intervention was superior with respect to the other. When we look a little bit more on the, so we try to make it binary, the primary outcome, and we basically identify the gait speed, and we identified the percentage of subjects who clinically improved in the two groups. So basically, this plot here in the upper plot with the A letter here represent the percentage of subjects in the experimental and in the control group that clinically improved in terms of gait speed. So had a clinical improvement in gait speed. And we could see that the 73% of the subjects in the experimental group achieved this clinical improvement, while just the 36% of subjects in the control group achieved a clinically important improvement. And this two proportion was significantly different with a p-value of 0.0048. Then we also tried to evaluate two subgroups. So the subgroups of the older subjects, so just subjects with an age above 75 years. And although the 2% was at the same level, so was unbalanced, this difference was not statistically significant. And then we focus on the more impaired subjects, so just the subjects who were unable to walk or at a gait speed below 4 meters per second. That was usually considered strongly impaired in terms of gait speed. And here we could see that almost all subjects in the experimental group belonging to this subgroup improved. So we had 91% of clinically improved subjects and just a 36% of the control group. To answer to the question I see in the chat, no, actually we just did this evaluation on the primary outcome, but this could be interesting to do and could be easily done because I have, of course, all the, so we can speak about that. Maybe I can try to make this check and then.
Can I just jump in? Can you please repeat the question for the recording? Because when we post the video, the question
you're
will
right.
not be, yeah.
Sorry, you're
Thank
right.
you.
I'm not used to that, but yes. Yes, in the chat, I've seen that Molly Verrier asked me, did you also compare the percentage for BBS improvements? And the answer is no. I did not do this check because I did this just evaluation just for the primary outcome, which was the gait speed. Also because the BBS score could be mainly just in half of intervention in which we did the balance training, but this could be something that I could easily do, and we may try to get in touch if you are interested in that. Okay, I go ahead. So to conclude this first study that I'm just trying to, that I'm presenting you. So what we obtain is that our biofeedback multimodal training was not statistically superior to usual care. We found just a positive trend in favor of experimental group in terms of locomotion recovery. And we also find that patients initially not able to walk might be the best candidate for such a training, which was actually indeed focused at the beginning for patients not able to stand and not able to walk. Since we really wanted to focus on a seated balance for seated FES cycling at the beginning for this reason. While if patients are already able to practice gait training, probably they can just be involved in gait training, and of course they can achieve, and not of course, but of course, and they could achieve similar improvements. Anyway, what we concluded is that our multimodal biofeedback training, being task-specific, repetitive, and intensive, and requiring a minimal supervision since it is performed in a complete safety situation, can represent a good alternative for early stroke rehabilitation and could be easily also performed in group sessions. So it could be a complementary treatment, important treatment for stroke rehabilitation. I don't know if there are also other questions about this first RCT, or randomized control trial that I'm presenting. Otherwise, I just do a step forward. So in the recent year, so after my experience, usually, okay, yes, there is another question that probably I can try to answer. So do you have an hypothesis as to why individuals with less impairment benefit less or do not benefit? So my idea on this is basically that all patients, they were involved in the same amount of treatment. And if patients were already able to walk, so there was not in this type of, in the control group, there was not any type of robotic gait training. So they were performing gait training, standard gait training with the physiotherapist, so not with body weight support or exoskeleton or type of robotic devices. So if the people were able to practice with some aids, gait training with the help of a physiotherapist, they probably do not achieve an additional improvement with respect performing FES cycling training. But if people were not able to be involved in this type of specifically gait training because they were probably more impaired, then in this case, we could see a higher improvement for the intervention groups. So, so when I was speaking with the clinician at our about the results, they were even, let's say, surprised that less impaired people, so the one who were already initially able to walk, achieved similar improvements with respect so in the experimental group with respect to the one who actually practiced gait training. So they were a kind of positive surprising, even if we did not find an additional improvement. We did not use ABC. So the question is here is, did you use any patient administrated outcome measures such as ABC? No, we did not include this type of measurement. And with respect to the other question here that I've seen here is, did you have any indication of differences in muscle atrophy? We did not measure specifically. So what we measure in terms of, let's say, strength was just the forces produced during pedaling. We performed, so with the force sensor that we have at the bike, we also perform at the beginning and at the end of the cycling training a specifically pedaling test in which subjects we were pedaling individually, they were pedaling voluntarily with no FES, and we measure the work produced by the two sides. And if I remember well, we found a significant improvement in terms of work produced by the affected side for people involved in the experimental group. But we did not have any, so this was the only measure of strength that we included. I don't know if there are other questions on this topic, otherwise I go ahead. And so starting from the experience, our experience on FES cycling, we moved from stationary ergometer to mobile trike. Indeed, when practiced outdoor, FES can become a recreational activity for stroke survival and mainly for people with spinal cord injury. And this could combine the benefits of FES with the physiological benefits of sport in a sort of, and build what we call sport therapy. And in this framework, we participated as Polimi to Cybathlon. I don't know if you are familiar with Cybathlon, but Cybathlon is a unique competition organized by ATH in Zurich. Today, here in 2020, in 2020, there were the second edition of Cybathlon. So the first one was in 2016, and the second one was in 2020. Unfortunately, of course, we could not really that this Cybathlon competition was not performed in person, of course, due to COVID, but they organized a global edition in which everyone was competing at his own place, and then they share results and compare results between people. And so this competition is this Cybathlon is a unique competition in which people with disability compete against each other to solve everyday tasks with the help of technology. The goal of the Cybathlon organizer is to promote research, development, and implementation of assistive technologies for people with disability. is to develop a common platform for technology developers, and is to inform the public about the scope and limitation of current assistive system, and to break down barriers between the public and users and the developers, and encourage inclusion and equal opportunity for people with disability in daily life. So far, Cybertron has been composed of 6 disciplines. So there is brain-computer interface, power leg prosthesis, powered exoskeleton, powered wheelchair, power arm prosthesis race, and functional electrical stimulation bike race, FES bike race. And specifically, we participated to this discipline, so to FES bike race. And the global edition took place in November 2020. And in this discipline, persons with a complete spinal cord injury, so complete loss of motor function, compete using a passive trike and a multi-channel neuromuscular electrical stimulator. And in this picture, And in this picture, you could see our prototype that is basically composed by a recumbent trike from the eyes. So it's a passive commercial trike, but we equipped with an angular encoder. So we included an encoder here in order to use the crank angle in order to module stimulation. We used 2 remove stimulators that were placed at the back here of the seat. And in order to be able to stimulate up to 8 muscles for 4 muscles per each side. We added 2 ankle foot orthoses at the pedal in order to prevent lateral movement of the leg while pedaling. We added some buttons at the in order to allow the patient to be able to the pilot to increase and decrease the stimulation, to start on and off the system. And of course, we have also an emergency button. Our control system was embedded on this box that was attached on the back of the seat. Of course, all the device has to be mobile. And the control system was running on a Big Bone Black, so an embedded control system. And then we had also an Arduino that was controlling a visual display, which was placed here in front of the pilot in order to show the cadence, the amplitude of stimulation, the time of stimulation, and some useful parameters for the pilot. And that's all. So this was our prototype. In the next slide, I have just a video that was a small summary of our participation to Cybertron 2020 Global Edition. As I told you, basically every one of us compete has his own place. And here you see that our trike was mounted on a smart trainer. Sorry, I don't know what I did. So indeed, of course, since we could not compete all together with the smart trainer that was the same for all the teams that was provided us by the organizer. They measure the distances that every pilot was performing, and then they compare the distances between every pilot, and then they create, of course, they compare the performance races. Here you can see our pilot, that is a T5, T6 lesion happening. The accidents occurred in March 2019. The pilot is an Asia A, so no motor and no sensory feedback. And actually, due to COVID, we could really train for a very short time. So we could train just for 2 months, twice a week. And our performances was not the best, so we did not achieve the final objective of the race, which was to perform 1 kilometer and 200 meters, but we could perform 860 meters in 8 minutes. We were kind of, anyway, very, very happy due to our very short training. And our pilot was also very satisfied, and so he stayed with us. He went on training twice a week for all the months till summer. summer holiday. So now he's on holiday with his family and his kids. And we could even able to, we could able to start training outside. So here you could see that we were running during spring, of course, outside with the trike. And so let's hope again to have the possibility to compete again. And we are really going on. So we are also now training a second pilot. So we found a lot of interested by spinal cord injured people in practice this type of activities. So we will go on this application. Again, I don't know if there are other questions, question on this specific topic. Otherwise, I will move on to the next one. So, but you have time also at the end. So when I was speaking before, I spoke about technology-aided approaches. I spoke about FES, and I said that I will focus also on robotic devices. And so now let's speak briefly about robotic devices for stroke rehabilitation. And so just for a big picture, I want just to give a classification between two types of robotic devices that can be classified from a mechanical design in end effectors and exoskeleton. Oh, I'm a bit late. End effector and exoskeleton. And so here, so when we speak about end effector, we say that they apply mechanical forces to the distal segments of the limb. And the main advantage is that they are very easy to set up and control, but they do not control proximal joints and possibility of normal movements. And there is the possibility of abnormal movement patterns. While exoskeleton are defined as the robot axes are aligned with the anatomical axis of the subjects. And here we have a direct control of individual joints, but the system are more complex and expensive. Here I have just some picture of end effector and exoskeleton from commercial devices for the lower limb. And while for the upper limb here, some example of end effector and exoskeleton, which are divided into active and passive devices. The main advantages of rehabilitation robotics are that they can assure high intensity, high dosage training that can allow to real-time monitoring the performance of the subjects and reduce the effort of the therapist. But the disadvantage is that they have a reduced wearability, they can be very big, so high encumbrance. There is a possibility of the so-called slacking effect, since the patient can be just let the robot do the job, and the workspace could be limited by the constraint imposed by the robot. From a therapeutical point, in terms of therapeutical effects, what has been seen is that lower limb rehabilitation robots, so for the lower limb, robotic gait training in combination with physiotherapy might improve recovery of independent walking in stroke survivors. And then seems that people in the first 3 months after stroke and those who are not able to walk seems to benefit most from this type of intervention. And this is a little bit in line with what we have seen before for FES cycling training. While for the upper limb, we have seen that stroke patients who received robot-assisted arm and hand training after stroke might improve their capability to perform activities of daily life, arm function, hand function, and strength. But these results were mainly achieved by using hand effects robots, while there is still a lack of evidence about the effects of exoskeleton in terms of randomized control trial. What I want to mainly highlight is that robots do not replace the rehabilitation therapy performed by physiotherapy, but they are just a tool in their hands and never rehabilitative per se. When functional electrical stimulation and robotic devices are combined, then we call these two combined devices, these two combined technologies as hybrid robotic systems, which are systems that rehabilitate or compensate motor function through the combined action of muscle activation with FES and mechanical and electromechanical forces supplied to joints. And if we go back to the picture I've shown before about neuroplasticity, we could see that hybrid robotic systems just usually are able to fulfill all the elements that we have listed before. And so they seems to be a very promising technology in order to improve neuroplasticity after stroke. For what concerns hybrid system for the lower limb, the main challenge is to design a cooperative control system between motor and FES. Indeed, what we could find so far in the literature is that we have the control system of a robot and the control system of FES, and the two are just combined one on the other, one on the top of the other, but the two control system does not speak with each other. While the next challenge to be solved in order to really exploit the full potentiality of hybrid system for the lower limb is to design a cooperative control system. This can allow to minimize the motor torque, to postpone the onset of muscle fatigue, to prolong then the intensity of the training, and to maximally exploit the benefits of FES. Indeed, as I told before, the current state of art is that we usually have a feed-forward control of FES and the feedback control of the motor that assure the tracking of the trajectory. There are a few examples of comparative control just for the single joint, mainly the knee. And multi-joint cooperative control system usually do not adapt to muscle fatigue. So I'm just keeping these two slides because I've checked the timing, so I don't, if someone then had some more question on this typical example of the literature about the hybrid system for the lower limb, I can go back to this. For what concerns the upper limb, in the literature we can find hybrid robotic system in which FES is combined with active robotic system or with passive mechanical supports. So starting from active systems, just a review of the literature, just going through the literature, we could find that FES mainly is used for grasping and hand opening, while the robotic device supports the arm weight and moves the arm in a 2D or 3D workspace. In few studies, FES and the robot act on the same joints, but none implements a shared control, and no methods to compensate for FES-induced muscle fatigue are implemented. Indeed, FES is usually controlled in an open-loop modality. Concerning combination between FES and passive mechanical support, usually the passive mechanical support provides arm weight relief. So the passive robot is used to support the weight of the arm. FES is applied both to arm and hand muscles, and both open loop and closed loop approaches are implemented, and FES can be patient triggered based on EMG, VCI, or eye tracker. But again, no shared control can be implemented because between passive devices and FES. Among the several examples, I want just to focus on the RETRAINER system. RETRAINER was a European project carried out by my research group, and is an example of passive hybrid robotic system. You could see here that we had a 4 degrees of freedom passive exoskeleton that was able to support the weight of the arm. And the 4 degrees of freedom were the shoulder rotation and elevation, the elbow flexion extension, and then there was the possibility for trunk inclination in order to increase the workspace. This system was combined with functional electrical stimulation, which was EMG triggered. So based on the same, the activity of the same stimulated muscles. So you could see here that we measured the EMG of the same stimulated muscles. And the muscle we could stimulate was the biceps, the three deltoids, and the triceps. As I told, it was an EMG trigger. So if you look at this plot here, that was the volitional EMG. So the EMG after the removal of the stimulation artifact. And as soon as this EMG overcome a threshold, here you could see that stimulation starts up to a predefined maximum value. And we measure also the voluntary EMG activity during the stimulation phase. And if this was above a certain threshold, then we show an happy smile at the end of the subjects that is shown here in this graphical user interface. Otherwise, if the subject was just let FES do the job during, then we show a sad smile here. This was the graphical user interface that was used both for setting the exercise and for showing the feedback to the patient. There was also a set of objects and RFID in order to identify so you can see here that we had several targets here, and when the arm reached the target, so there was an antenna placed on the exo at the end level, and then when the hand reached the predefined targets, then the exercises went on. So probably it's more easy to have a look to these video. This was one of the exercises. There were many exercises supported by RETRAINER. This was just anterior reaching. So the exercise was divided into subtasks. And so the subject was guided by the graphical user interface through the different color of the target. So he had to reach the yellow target, the red target, the blue target, and every time he has to go back to the green target, which was the rest position. And this was repeated many times, and then there was also other exercises. And also in this case, we performed a randomized control trial in which basically we included patients with a first stroke 2 weeks up to 9 months before enrollment, so in the post-acute phase. We asked that they had some activity, so we measure the Muscle Research Council of arm and shoulder muscles of the affected side, and this has to be equal or more than 1. We required that participants had a low spasticity of our muscles and that were able to collaborate. At the end, we recruited 68 post-acute stroke patients, which was randomized in the 2 groups, the experimental group performing exercises with retraining plus advanced conventional therapy, and the control group performing just advanced conventional therapy. Both groups trained for 90 minutes, and in a total, we had 27 sessions, so 3 times a week from 9 weeks. The advanced conventional therapy consisted of upper limb, passive or active motion, arm cycle ergometer without FES, FES of forearm muscles, but no FES of arm muscles, of course, virtual reality, augmented arm exercises, repetitive task training, and mirror therapy. This was the outcome measure, so that was classified between body function, activity, and participation domain of the International Classification of Functional Disability and Health. And the primary outcome was the action, so the action research arm test to evaluate arm functions. Also, for the experimental group, we measured the usability of the system. Participants were evaluated at baseline, at the end of intervention, and 1 month after the end of the intervention. This is the picture summarizing the characteristics of the patients at baseline. They were similar, particularly they were about 2 months after stroke in average, and the mean age was about between 60 and 68 years. Indeed, as you could see here, that the control group was a little bit older than the experimental group, and this was statistically significant. So the group was similar, but for the age. Indeed, we included age as a cover rate of our statistical analysis that is summarized in this bars plot here. So what we could see is that for the ARAT, so the primary outcome, we could find as an improvement over time for both groups, but also an interaction significant effect here. So the p-value is 0.002. This means that the experimental group achieved a higher improvement with respect to the control group, and this was maintained till the end of the intervention. For what concerns the motricity index, we had a similar improvement for the 2 groups, so a similar significant improvement for the 2 groups. With respect to for what concerned the box and block test, evaluating the dexterity, again, we had higher improvement for the experimental group with respect to the control group. We measure also activities of daily life, with evaluating the motor activity log, quality and quantity subscales. And again, here the improvement was similar for the two groups. And finally, we evaluated the quality of life. And here we did not observe any improvement for both groups. So none of the group had a significant improvement in terms of quality of life. So what we concluded at the end here is that training with RETRAINER was superior to advanced conventional therapy in improving arm function and dexterity in the activity domain. Also, patients consider RETRAINER moderately usable, so the system usability score was about 60%. And so at the end, what we concluded was that the reason why RETRAINER was, we thought that RETRAINER was superior to advanced conventional therapy, it could be summarized through the novel aspect. It can apply a personalized and task-oriented exercise. It enhances sensory feedback thanks to the use of FES. It includes both shoulder and elbow movements and promote voluntary engagement of the subject, and require also low supervision of the therapist. Overall, what we observed was also that there was still an overall limitation in transferring functional improvement to real life scenarios, because we do not observe actually significant the same improvement in terms of ADL, so activities of daily living, and mainly we do not observe improvement in terms of quality of life. So just to conclude, I want just to highlight which are the main challenges for hybrid system, in my opinion. So what we need to work mainly is to design interacting and share support between robots and FES, and eventually also with volitional contribution of the patients. The control should adapt to muscle fatigue, should adapt to patient progresses and performance, and should provide the minimal support in order to allow a correct execution. So it should implement the so-called assist as needed control system. We need to improve wearability and minimization of the encumbrance, possibly reducing motor size and weight thanks to FES contribution. And we should optimize the calibration procedure, because when I'm speaking about hybrid system with physiotherapists, the main question is, okay, so now I need to calibrate two, so I need to set and calibrate two systems instead of one. So both the robot and FES. So we should really try to find a solution also from a very practical solution also, that we do not prolong too much the time for wearing the system. So electrodes should be textile electrodes, probably just included into the brace of the motor of the robots and so on. So we should not avoid to really double the time needed for set up the two systems. And mainly for the upper limb, it is very important also to try to transfer the improvements to real life scenarios. So we should add virtual reality, interaction with real objects, a 3D workspace, in order to really try to get the improvement, the functional improvements to the level of daily life activities. And what's next? What's next is basically that rehabilitation should really go home with the therapist's remote supervision. And this could be probably be able thanks to the use of exosuits, which are light, low cost, wearable, high comfort, safe, since do not require joint alignment, and could eventually integrate textile electrodes for FES. And we might exploit also the use of artificial intelligence for calibration and detection of the user intention. And with this, I want to conclude and thank you. And probably I was also a little bit too long, but I answered already some question, and I have seen that I have already other questions to answer. So there was one here. Can you please share how much the active and passive robotic device cost approximately? This really depends on the system. So the one of RETRAINER, of course, is not available on the market since was a prototype developed in the European projects. There are some other devices, for example, the Armeo, but I have to say that I cannot say exactly the cost of the devices because they're the commercial device. That depends.
Thank you very much for a wonderful talk. It's almost 1 o'clock. You've answered a number of questions during the presentation, but I know some people might want to leave at 1. So for those people, let's join me in a round of applause to thank our speaker. And in case you can stay and have questions, please stick around and type in your questions. And maybe I can ask a question to start. Can you talk about the engineering challenges of designing and implementing this in the lab? Like, I'm running a robotic rehabilitation device individually and a FES device individually has a lot of challenges. Did you have any particular challenges in synchronizing the two and running them in parallel at the same time?
Okay, so in terms of computational, I think this is not the main challenge. I don't know if it was the question. So, because I mean, so far, even embedded control system really have a very high power. So I have to say also because FES does not really require usually high frequency signals. So I think that this is not the main. So the problem of synchronization is not the main issue, in my opinion. Really, the main goal that we should have, in my opinion, is that we should really be able to integrate the two technologies at the low level. So what I was trying to mention before was in the hardware part, we should really avoid to ask the physiotherapists to wear two different technologies. And currently we are at this level. So currently we have seen that hybrid robotic systems are promising from a therapeutical point of view, but at the current stage, they are just one on the top of the other, both in terms of control system and both in terms of hardware. So what we really need to work from an engineering point of view, in my opinion now, is really to try, and this is not that easy because usually these two communities are separated. So there is a very strong robotic communities, and then there is people working on FES. So it's not that easy to really combine these two technologies at a low level. So we should try to build multidisciplinary team and try really to think. So once we have demonstrated the capability of the potentiality of this combined action, we should then go back and redesign maybe the robotic devices in a way in which it really integrates the FES component, both at the level of the control system and at the level of the hardware. Thank you.
You kind of alluded to exoskeletons for home.
Yes.
And that would be a mechanism to include both robotic and FES, I guess. And maybe hopefully in a couple of years, we'll invite you again to speak for us about your exoskeleton results. We have a question from Milos. Oh, no, it's just saying thank you for an excellent presentation. And there's another question from Gustavo. Do you want to read and answer that?
Yes, thanks for the talk. What is your opinion about the use of surface EMG to assess the FES intervention efficacy? How do you compare pre and post functional electrical stimulation therapy surface EMG data? Yes, I definitely think that surface EMG can be used to assess the efficacy of FES. And I've also done some studies in which we evaluated EMG before and after FES study. And but I think what I don't know if this is what is included in this question. Usually, I think that EMG could be used to evaluate motor coordination or anyway so the timing, the coordination of the execution of the task. And So this could be done before and after without FES. So I think that EMG in FES application could be useful both as an assessment and also during the intervention in order to evaluate the real involvement of the subject. And in this case, it's a little bit more challenging since we need to adapt to include specific filtering of the EMG signal in order to cancel the stimulation artifact.
Thank you. I think we're 5 minutes past.
I speak too much, sorry.
No worries. That's perfect. I really enjoyed your talk, and I think judging by the questions during the talk and afterwards, it looks like everyone also enjoyed your talk. And I think we can wrap up at this point. And I thank you again on behalf of our institute and everyone and myself. Thank you for a wonderful talk.
Thank you.
Everyone in the audience, please join me in a final round of applause and to thank our speaker.
Thank you.
Bye.
It was a pleasure for me. And maybe sometime I could also visit you. Who knows?
That would be wonderful. That would be wonderful. The next talk will hopefully be in person.
In person. So thank you for the invitation and for
Bye.
Bye-bye.
Thank you again. Bye.